Yeah, so welcome everyone to the online audience and also to the ones in the room to our interesting lecture on deep learning. So some of you maybe noticed that we have a whole lecture series on deep learning given by Magnus in another department. So the idea here today is not to give you a one-time lecture and discovers everything and every little detail of deep learning. However, it is true that deep learning is one of the key drivers of using big data in clouds today. So I will make the case on a relatively moderate level, and we'll also go in the next lecture, in lecture 7, into some of the details of what are convolutions, weight sharing, and so on. But today we kind of mobilize this a little bit from our lecture 2 perspective, where we started with a very small neuron, if you remember, the perceptron learning model, and will extend to cutting edge deep learning, because essentially they have lots of overlaps and are the key building blocks of that. When we go back, however, what we did the last time, just to connect from all the material we have here in the lecture, we started with an interesting big data analytics approach, as it is called, this kind of MapReduce framework. And you learned by now that map and reduce is not the full story, right? The full story is that you have grouping, shuffling, and sorting in between. And this is done by the framework, enabling us very nice applications with a minimum of implementation work. So we just have to provide the map implementation, we have to provide the reduce implementation, have a little bit of an agreement on the keys, like word count, right? We want to just for every word occurrence a 1, very easy to implement, and then aggregate the results. Very nicely done, but the whole distribution in this all distributed framework across all the different nodes is something we have not to implement. There's no communication by us done. Everything is done by the Hadoop framework. And this is, of course, a beauty. If that compares, to HPC, where we do really explicit communication, we say exactly to which we want to communicate, right? And this is a key difference, and also enabled lots of, let's say, update of this cloud in more usability point of view. So it's much more simpler to use a cloud with these programming paradigms. And I provided some demonstrations how to use AWS. Again, I'm sorry that you cannot really use the EMR anymore, because essentially we learned that all of those have decided to put essentially the MapReduce framework not anymore in the educational package, but at least I could provide you with an overview in the demo when you swipe your credit card. By swiping the credit card, you have seen it was all working nicely and the clusters were running. Always be advised that the clusters that you run when you want to try it out with your credit card keep on running. And with this, keep on charging, right? So what we have seen there for a GPU like 28 bucks per hour could quickly accumulate to a hell of a lot of money. Then we basically had, at the end of the lecture, also understood a little bit, at least, the different ideas of scaling up, scaling down, hence elastic MapReduce. So we could always increase, let's say, the number of workers that you see there, which in the end are just EC2 workers, although there's MapReduce on it. So elastic compute in terms of single CPUs or GPUs, but on top of it was basically then this Hadoop framework rolled out. And that's why we always had to wait in the beginning until actually the whole deployment takes care. We have also seen nice examples of auto scaling, where you then can basically have different options where actually the cluster can shrink down and up if you want. And this is, of course, very interesting for us in the different workloads. If you buy your own premise resource, big HPC machine in your cellar, this is, of course, different. You have it always there. Even if it's 99% idle, you have to buy the costs, have all the costs for the operations, the administrators making security updates. And here you can just simply scale up and scale down. Good. And with this, I think you have a very big cornerstone done also in this particular course, because we put the very relevant topics early for the assignments. And I think MapReduce, when you go to a job interview and can explain that, it gives you really good chances, because many of the big data analytics workload today is based on these facets. Let it be Hadoop or Apache Spark, they're very close to each other, as we learned already at the beginning of the course. Knowing both, you will see when we have the epilogue of the course, will be always in job applications around data scientists today. But let us come a little bit to deep learning today. Again, a short disclaimer, learning deep learning just in 2 lectures is quite tough. That's why we do it on a moderate level. It's not really that I can show you all the benefits of deep learning, and we focus on a certain area of deep learning for image recognition called convolutional neural networks. But in order to go there, we have been stopping by a normal perceptron, by one neuron. We now have to first understand what is the idea of connecting them, making them so-called artificial neural networks. Also, known as multi-layer perceptrons. So we look at this and always pick up on that, what we also had in basically very beginning of the course, where we said, what is the idea of this MNIST data set of the image recognition, basically from these different digits, right, in the 10 classes. So we go gradually, slowly, step by step from the simple perceptron, a multi-output perceptron, actually then to artificial neural networks. We will compare the performance in terms of accuracy. And then we will see basically that the second part here is then the introduction more to this deep learning, but in a very applied sense, right? So Magnus and others would probably put first a big tensor building block in terms of theory in front of it, and things like what is a convolution operation. I try to do this here in the cloud sense, relatively on a moderate level. And then we will revise certain techniques in lecture 7. And actually we will have also an invited lecture 7.1 from Rocco, one of my PhD students, who then shed light on other perspectives of this. It's a very important topic. Also here, if you go to a job interview of data scientists, cloud computing, big data analytics, and don't have a skill set, a little bit of deep learning would be bad, right? So in an interview, this would be one of the next questions, because today deep learning is really applied to sequence data, to image data. It's a very important technique. I also encourage you to study it very further. We have tremendous results in research based on deep learning. With Thomas Philipp, one of our professors here, we said like 5 or 6 years ago that this is a whole hoax, because we knew before that deep neural networks would be, something which people have used in the past. But now it's really a momentum, and we have really perfect insights from all sorts of directions, from sequence data, image recognition, everywhere. But let us come a bit to this artificial neural network. So basically that is before deep learning started, and we need to understand this in order to hop to the deep learning later. Just to revisit, so we said here we do a little bit on supervised learning as a focus, and supervised were largely characterized by this vector of X, having all the features in the data, and then this guiding output label Y. So this is important because then the supervised learning can always correct and basically measure the error that we do when we, for instance, do a pointwise error calculation. And what we did there was essentially this use case, if you remember in lecture 2, right? We had the idea of a simple line, which we could actually create very interestingly enough simple with a so-called perceptron learning algorithm. And it found a decision boundary over lots of converging by adding and subtracting a vector, flipping all the time, yeah, basically by -1, +1. And if you do this often enough, 10,000 iterations, 100 iterations, a million iterations, you eventually converge if the data is linearly separable. And this is a word which we also have to pick up today. So this is loaded, because many of these lines that we want to have in machine learning are exactly not like that. We have highly non-linear data sets. So the perceptron is at the end, right? It's just a linear learning model, so we cannot advance it further. We need to build something different. And that's why we take the construction as a perceptron model that we had already before. It still remains essentially linear, but we put in terms of this typical sign that we had, the step function, or in logistic regression, a logistic function, we put here nonlinear activation functions and take them as a Lego block, right? So as a kind of bits and pieces to really build something bigger. And the rest of you, X is a constant, it's the input data set, and these red things, the weights, is of course what we want to learn. As an example, we connect to what we had already actually in practical lecture 0.1, where I showed you a bit the benefits of Python. So now we connect to this again. You can download this simply in Keras, just basically with one kind of small command. Then you have the data already inside these deep learning frameworks. And by now, it was also part of the quiz, you know exactly what this idea of this multi-classification is. But of course, now the point is, again, we had the flower, Iris setosa, Iris virginica, 2 classes. But now we have 10 classes, 0 to 9. Right? So also here we see already we must have a better model in order to do that. So still general concepts remain. We want to look into the data like we also have in practical lecture 1. We see there a kind of 2D input. That's what an image is, essentially, when I put a digit in, which is an important consideration we have to work on as well, right? If you just do the data inspection, you see essentially the strengths in the paintings, and so characterized by numeric values. And we have always this nice grading label that tells us in the end, this is a 2, that is a 5, that is a 9, etc. The principles also remain here, that I have to put training and test sets. So we largely take what's there existing. And of course, this is basically a, let's say, relatively fast forward through this. That's why in the assignment 2, you will basically do this all yourself again, right? So the material I show you here is directly relevant to assignment 2. It will be a bigger assignment. It's actually 20%, not 10%, and will be until the end of the semester, because deep learning is also a topic which is not so easily digestible. I know, but it's still very important that you at least get the groundwork on this done. So when you go to job interviews, that you know a little bit about it. So we have here 2 frameworks. Keras is basically on top of TensorFlow to make it a bit simpler and layer-wise. You could also do the same thing directly in TensorFlow, but Keras is quite often used in teaching and make it simpler to follow. You already had this introduction before. And of course, if you want to try out basically the examples and so on, you could go to the Google Collaboratory as one example. You have used this already, where you have then also GPUs available. This is important for deep learning later. But of course, also we will see that the AMI cloud, that will be part of the next lecture, lecture 7. We cannot stress and put everything in this lecture. There we will look a little bit more behind what is this, let's say, deep learning AMI, and why are these packages that are there provided already helping us to work in the cloud. So as I said, it's a kind of complementary setup then in lecture 7 to go much more into the cloud part, while we focus here a little bit of understanding the deep learning part, right? So what is it with deep learning, why we need to use this? Now, when we go on and have some, let's say, hands-on approach of using this, you have here the idea of printing out in the Jupyter notebook. If you do it in a collaboratory or an AMI, doesn't matter, of having, you know, a small script that you see the kind of the images. That's what we did already in practical lecture 01, of really understanding the data set. And when we understand it by the output, we already observe many different things. One is that, for instance, it's 2D. Now, when I think about the Perceptron learning algorithm, that was not enough. I had a 2-class problem and also a 1D input, right, at that point in time. So we basically have here something where we have to work on probably to make it in a, let's say, more digestible format. And how you do this is essentially we still consider, of course, all the inputs here as one long vector, if you remember from our notation that we have. And then think about summarizing it as we did with the normal perceptron. But the problem is we cannot put a 2D input in a 1D vector, right? So here the stress is a little bit like how we transform now this in a very long vector in order to put it just into this perceptron, right? So basically there should be signal, 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 image by image by image, but I have 2D, so it doesn't fit. So I have to vectorize this. But this vectorization, unfortunately, is very much loaded, because when we do this, you have a very long vector. You lose all the spatial information in it, right? You have a 1D long vector, and you don't have any more these kind of, the surrounding pixels are all black. That means it's probably still part of the figure, right? Or of the digit. So this is a key problem that we will pick up in deep learning in the second part of the lecture, where actually exactly the deep learning algorithms are perfect in those to take the, let's say, supporting surroundings. So by doing this vectorization, we lose already information in the data which was given to us, which is not good, and that we will see in the performance. Another part of the story is now we basically can vectorize, and then we have, instead of this 28 by 28 pixels, we have a very long vector with 784 pixel values, basically. But what we also learned is we have 10 classes, right? So now the simple, logistic 0 and 1 binary will not work anymore. So we basically have to think about something else, which is called the so-called softmax activation, where you then also add different nodes again to probabilities of the different classes. That's also something which you now find in all the different neural networks, exactly this part at the end, right? So it's not only something for the normal perceptron, but here we actually adding something which is then used for all the different neural networks, which is a specific, activation function we can use to put all the probabilities of the classes. And by this, it's good when you create this in kernel. And as I said, you will do this in your own assignment, right? To get a better understanding of this. But you quickly will notice that the parameters will already grow, right? So because now, of course, I have 10 times the neurons to output, right? So basically the 10 classes to output, then I quickly come to learnable parameters, which are in the 7,850. To understand the growing of parameters is important for statistical learning theory, because this is something what we learn, and we have to have data to learn all these parameters. If you don't swim in data and have very little data, but have huge sets of parameters, we are very prone to overfitting or not learn at all, right? So this is something which I also want to encourage you to always monitor. What are the amount of parameters here, what we actually learn? And the learned is still here, the dense layer for all the different neurons connected, as we learned in the beginning. But now, of course, I have many of those, 10, because I have 10 classes. And then from each of this, basically, I take then the number of inputs from all the images coming through, which is this long vector of 784. But now I have actually a model that can digest the data. I have a 1D input of the image, losing spatial connectivity, okay, but we swallow this. And now, of course, I can do similar things like we did with a logistic regression, no problem. I use an optimizer that now can actually have a specific loss function satisfied, and basically taking the derivative and checking if we have the minimum. That's something what we already have discussed now, I think 2 lectures. So, but here, of course, we need something maybe specially prepared for multi-class label prediction, right? So here's something which is called the categorical cross-entropy error, which is just something we put out of our toolbox, which is usually used for these kind of problems. And the whole concept remains that we still have to observe the loss function all the time to check the learning. And we have the learning rate that determines how much we go, downhill with the derivatives. But still, the idea is to really think about a new loss function here in combination with a new model called Multi-Output-Perceptron. So we're not anymore really what we learned in lecture 2. We are now far ahead and can do multi-class classification. The script for this, you will play around in your assignment 2. There's a certain number of parameters that you have to configure, the number of epoch, how long or how often you actually go through the whole data set to train. When you have each weight update basically done this, I will come to this, how this is done in a moment with backpropagation and so on. But then the batch sizes, how much actually you take before you do a weight update to the different models. They have the number of classes, which is of course given, it's in your data set. And a couple of others you will basically play around with. You see optimizer, we don't have to use SGD. There are much more advanced optimizers like Adam or nested momentum. There are others around that we can use. Otherwise than this, you will normalize the data. Otherwise, you come quickly into problems maybe with data structures. If you multiply again, basically what neural networks do, they multiply and multiply again and again, as we know from the weights times the input. So here you basically exploding, and normalization can, for instance, helping you there in one respect. And then when we want to fit the model, you see that Keras gives us a nice area of sequential. We have a model where we have now a dense representation saying that everybody is connected to everyone else, as we have seen in the figure. All the 10 inputs, basically, all the long vector inputs is connected to every of these 10 neurons. And basically then we put this so-called softmax activation function in the list that puts out the 10 probabilities in the different classes. And when we compile the model, we take the loss function and the optimizers and just specify of what metrics we actually want, like accuracy, for instance. And then you fit the model. So it's very similar like we did in logistic regression, right? You just have other parameters, like we said already. The batch size matters a little bit, especially if you scale up very high. We do lots of research here, because then by very big batch sizes, the accuracy drops like hell. Then by number of epochs means how long you really train. You can also overtrain and overfit if you train too long. So it's also a parameter called a hyperparameter that you have to find out and steer. And of course, this is the most computational complex one, because again, we have this, taking the derivative, the optimization within, that is essentially then a problem in terms of computing. Just to give you again the visual exploitation, when you see number of epoch 200 instead of 20, you essentially could end up like this. Yeah, so this is what we call overfitting. Every single point is taken by heart if you train too long. As I also told you in the assignment 1, as a side effect, when you use regularization smartly and also validation smart, then basically this overfitting should not happen that hard, right? Because you combat basically overfitting with regularization validation. Of course, on the other end of the scale, if you do just one epoch, once through the data set, you underfit the data. That's also not time of the goal. So the sweet spot is to find, of course, the one that is actually fitting all this data right. And this is something which you don't know. You have to basically put and find the parameters similar like you have used basically the other regularization parameters and so on. So if you do this, and you will do the same in the assignment, you will notice that in the end, we have lots of iterations. Now we have to go to the training, basically the training set, then we do the validation, and we get some accuracy out of this, which is, let's say, 0.91, right? So this is something now as a yardstick of 90% accuracy, which is relatively okay for the, let's say, very, very stupid model we have. Right, it has almost none parameter, like 7,800, and it's just a linear, more or less, learning model. It did it added on with, let's say, this kind of multi-layer perceptron idea, but still, it's a very, very, let's say, simple model. So now you have to think about maybe it's already okay to do this with this model, or can we do more? Right, this is always a question. If maybe for the bank 90% is okay, then you take the model, give it to them, and you get the check. But of course, we could maybe do more of getting to more complex models. And that's what we want to do, going to neural networks now. Right? But by now we have still, let's say, a one layer, multi-layer, however, perceptron. And we have a good yardstick of 90%. Now, the trouble we into with these models is essentially very quickly understood by these, the idea. So in the end, you still remain with the linear approach here to a problem that some problems you just cannot handle, right? This is very famous, the XOR problem. So you have class B on these sides and class A on these sides, right? So there's no line that actually can make that. It's pretty clear, I guess, right? There's no dividing line that can do this right, as you see from the top. And you can play around. And so what would happen to the perceptron learning algorithm? It would fail. It would always not converging, right? It would forever going on. So now the idea of artificial neural networks is now, when we have just one line, what about connecting them? And this is what you see on the left-hand side, which is a very simple, tiny artificial neural network to connect different neurons. And each of these neurons is still, as we learned, right? A very small ingredient with linear inputs and then summed up linearly using weights. But then these weights are trained and put through a non-linear activation function. So this word is loaded. We come to this in a moment. But in the end, through this combination now of having one hidden layer, you can see it as we combine these lines now to achieve a certain goal. And you see here by these two lines, suddenly we are able to actually can have a class space that actually can do and differentiate, which would be not true actually by one simple model. And this is now the limit that we have in this, let's say, linear perceptron models and motivating the idea in the 70s of going to artificial neural networks. So by doing so, there's one important consideration, and this is really capture the non-linearities. If we would do still a linear function there, then actually nothing would change because the signal is highly non-linear. You see that as an example quite nicely above. Right on the top left, there would be always applying this linear function, and let's say we'll never do it right. While by applying non-linearities, and there are actually a couple of them to choose from these days, which is another hyperparameter set that you have to tune and can pick. Basically, very popular is the rectified linear unit, like or leaky rectified linear unit in research, for instance. But all of those can be now plugged in, and actually then, let's say where the signal comes through, catching this non-linearities. And by combining this, we still talk about this one neuron right here. But now I use a neuron with a nonlinear activation function, and I combine them now, of course, like Lego, as we've seen in the previous picture, by doing a whole set of them. And by using now not one or two, like we have seen in an example, but by basically in the script, you have seen maybe 128 in the lecture slides, right? We have 128 of those neurons in the hidden layer. I still have, of course, my input layer like the image, right? That's not what we can change. But here I can change a lot. I can actually have 2 second hidden layers. Basically, we say also with 2 hidden layers, you can do almost everything in neural networks. It just, requires lots of tuning. And then in the end, the output layer is often very similar in supervised classification. At least you have this softmax again, and this kind of winner takes all decision. That means that you have in the end just probabilities. So it's sometimes these neural networks give you 30% a 3, and maybe 70% a 9, right? So there's not always a 100% coming out. So you have to pick the probabilities and pick one, and that means the winner takes all, right? So the winner says in this class, but the truth is of course a 9, if you compare the 9 with the 3, it has elements from each other, right? And I have some visual idea also how I can show you this in a moment. Then how to train it. It's usually a complete lecture. Backpropogation is, of course, the training algorithm. If you remember, we had the perceptron learning algorithm, and then basically for the perceptron model, here we have artificial neural networks and backpropogation as the learning model. But essentially, what you will do is you always go in a forward pass through the neural networks you have. You can always compute what weights you just have with the signal going in, and then compare the error that you have. It's supervised, so we know it's a 3 or a 9, and can basically then determine the loss function. That's a little bit here, right? The output value that you obtained by the idea going forward, and then the kind of desired output, which would be our guiding label Y. It's here a little bit from another illustration coming, but still the idea is we have the ground truth and can then basically obtain the error with it. And by doing so, of course, through all the different samples, which is our N, basically I can now calculate essentially the loss. By doing so, that is a loss. Of course, the learning rate that I put then in by taking the basically gradient and so on, which is now basically the time consuming part in it, right? But taking all these gradients and so on step by step through all of them, I can basically determine with the learning rate how quickly I go there. You see a little bit the extreme situations on these, right? If you have a very small learning rate and I do an initialization, I step really little forward in this, right? So when I have this learning rate very quick, very slow to set the new weights. When I do overdoing it and have a very high learning rate, then you see I ping pong here all the time while I want to go here. So I maybe never reach the local minima of error of this loss function. So in a way, the learning rate is another of these parameters where this is, of course, something to figure out in your hyperparameter search, in your tuning. And today there's even some, ideas around it by making maybe it adaptive as a measure of momentum and, taking the velocity into account. But in the end, you achieve to something called the local minima of error, when you have it a bit as a phase where you basically go downhill. And that's what you then report basically as your weights. And this is obviously then the trained algorithm, just representing our red weights that we wanted. So looking at this in code, again, we structured now differently. We have 2 dense, basically ones. So that means every neuron is connected with every other neuron. We say how many hidden layers, we say which activation function. That's also what you play around with in the assignment. Here it's a rectified linear unit, basically just the positive ones are counted. Zeros is maxed to 0. Everything which is basically below 0 is basically getting to 0. And yeah, then you basically create very similar like we did. The input still stays the same, like in the multi-output-perceptron, right? So I have my long vector of pixels, and the right side stays the same. We have still this kind of softmax to go out, right? Which is then the probability of saying 10 classes, because I specify before that it has 10. And then all I change is now that I have a massive network in between, which makes it this artificial neural network or multi-layer perceptron if you want. And by doing so, and doing this in the script, as we just have seen, we come to an accuracy like 0.97%. So we see just by putting lots of neurons in the middle, And using nonlinear activation functions with this neural network, we are able to improve massively. In machine learning, usually a percent can mean a lot, right? And now when you do this and basically do some validation across, you see the effect of basically reporting something which was not completely true. So here you see the effect of reporting less than you probably just get with training, or having 95%, which is still very good after 20 epochs. So this is now the yardstick compared to the multi-output-perceptron, a much more tough model. You see directly we have now 118,000 parameters to train, weights to train. Before we had 7,000 to train. And there is, of course, now the complexity of computing, why we need cloud computing, because you can imagine when we now move in the second part of the lecture, then to deep learning, we will increase there massively on weights and number of parameters. Just to give you a short summary on this, I brought you a video, but as I said, if you don't understand everything completely, don't be worried. We pick up in the next lecture, I mean, in the second part of the lecture, anyhow, some of these things. And in the lecture 7, again, you will do it in your assignment 2. You will basically have an invited speaker in lecture 7.1. So this is the progress and, something where you have to, of course, think about it step by step and come to the knowledge over time. So this is a nice overview, and maybe then we can get to the break.
This is a simulation of a single biological neuron. Information flows in, is processed by the neuron, and the results flow out. This gives the neuron its abilities to react based on previously learned patterns. Technology duplicates this by creating a structure that processes information like a biological neuron does, except this process is mathematical instead. Just like the biological neuron, information flows in, is processed by the artificial neuron, and the results flow out. This single process becomes a mathematical formula that can be used for simple problems. For those that are mathematically inclined, this will look similar to a polynomial. A polynomial is limited to the problems it can solve for, as shown in this graph of an order 5 polynomial. If this is all artificial intelligence could do, it wouldn't be much use. As with a brain, artificial neural networks' power is in connecting sets of neurons together in layers. When you connect them in layers, the mathematical formula becomes something like a multi-dimensional polynomial. This allows complex problems, like what is shown in this graph, to be discovered and used for our benefit. As before, information flows in and results flow out, but this time the input to the second layer is from the output of the first layer. The exact steps for a single layer are simply repeated for each layer of the neural network.
So, okay. I hope that summarized at least a little bit of that. Arguably, this is a very complex technique. Of course, neural networks, as I said earlier, they can essentially learn everything. Just takes a number of time to train and do hyperparameter optimization. So we break here for 10 minutes and then repeat after the break with more deep learning and see what deep learning can do.